Very good. Thank you very much for the introduction and for, yes, I wish my wife was here. I want to thank all of you for coming, and special thanks for my good friends from Mainz who bothered to come all the way here. I really appreciate it. It's really fantastic. I changed a little bit. If you notice, I changed the title a little bit. Instead of mentioning 50 years of cloud seeding in Israel, I made it 60 years for cloud seeding worldwide. I will concentrate on the Israeli case, but I will also give examples from other places, which I think will give us a pretty good, I would say, understanding, although it's quite controversial. I think will give us good understanding of what's happening and what should be worried about when we go and do cloud seeding. The picture I have here, those red flowers, we call them kalaniot, they come immediately after the rain, the early spring. So this is just an indication of the cloud seeding. Hopefully we get more of those flowers. Why do we talk about cloud seeding? Well, in response to global warming, water shortages in many places have been forecasted, especially in the Mediterranean region, but also in other places that are far away from any source of even ocean or sea. And people go and try to look for different methods of producing fresh water for drinking and for agriculture and industry, of course. And cloud seeding is one option that people have used. According to the WMO, there are presently about more than 80 projects around the world dealing with cloud seeding for rain enhancement. Unfortunately, most of them are operational and not scientific, and I will talk a little bit more about it. So why do they go to cloud seeding? Well, it is cheaper. Just to give you an example, in Israel they did once a calculation, an economic calculation of how much does it cost to produce 1 cubic meter of water through cloud seeding, provided you get a 10% increase in precipitation. It turns out about 2 cents per cubic meter. And this is compared to about 50 cents of desalination, and maybe about 30 cents if you want to purify purify brackish water. So it is considerably cheaper, and therefore water managers in many countries don't bother even to think about the science behind and whether this particular practice will produce more water. They say cheap enough, and therefore we can go out and do it. What I will try to talk about today is give you a little brief history of the subject. I will talk about cloud seeding for producing rain by what is called glaciogenic seeding, which means ice nuclei. Talk about the Israeli cloud seeding experiment and experience. Some of the reanalysis of the Israeli cloud seeding, which actually put things in with many question marks. I will talk about hygroscopic seeding, explain what it is, and give examples of hygroscopic seeding experiments in South Africa and Mexico, and then, of course, summary. I will start by pointing out a book that is available, if you want. It's called Fixing the Sky, The Checkered History of Weather and Climate Control. In fact, most of the book deals with geoengineering rather than with cloud seeding, but it does have cloud seeding in it with many anecdotes. It's a lot of fun to read. I picked a number of issues that he mentioned, which I think relevant to this place. First one is about Robert St. George Derringforth. Think about this guy. He was a PhD in mechanical engineering, and he received $9,000 from the US government. This is I'm talking about in the 19th century. $9,000 was a lot of money. The objective was to carry out experiment on rainmaking. Now, why did I pick him up? Well, he was born in Chicago, but was educated here in Karlsruhe. in the Polytechnic School in Karlsruhe and also the University of Heidelberg, and received his engineering degree in mechanical engineering. By the way, then he went back to the States and became a lawyer also. So I'm not sure it's a good combination, but that's what it was. His idea for making grain was something that we wouldn't even dream of doing it today. He called it concussion, but actually it was explosives. He used dynamite, he used rockets, he used, balloons and kites, mortars, smoke bombs and fireworks, all around. It was a, complete operation. And he did an experiment north of El Paso in Texas. There was no rain coming out of this experiment, but the rain happened to fall south of El Paso. Well, of course, in all the newspapers he claimed big success of cloud seeding, although the winds were blowing from south to north. But it doesn't matter. All the newspapers loved it, and that's how it was. So I decided to point out that you also have something to do with it. Then something about the origin of modern cloud seeding. By the way, if you read the book, you'll find many other examples of people trying to paint the desert black to create more convection and all kinds of other funny things that are, but I will try to stick to the serious stuff. The modern experiments in cloud seeding actually started in Schenectady, New York, in the GE, General Electric Laboratory. Langmuir, Erwin Langmuir, who was a Nobel laureate in chemistry, and Vint Schaefer, who was his assistant, had no experience in cloud physics, but they dropped some pellets of dry ice into a refrigerator and observed little ice crystal form, and they watched it for a while, and the ice crystal fell to the surface. Wow, we can do the same thing in clouds. We can throw pellets in clouds, and rain is going to fall. So this led to the speculation of rainmaking, and in November 1946, they dropped 3 pounds of dry ice pellets into a supercooled stratus cloud at about 4-kilometer altitude, at about -20, flying in a racetrack to prove their point. Here is the picture of their experiment in General Electric. This is the cold box, and what you see here on the top there is this is Langmuir, this is Schaefer, and this is Bernie Vonnegut, the brother of the author Vonnegut. This is what happens after seeding, after 20 minutes of dropping pellets of dry ice into this supercooled stratus cloud. Well, obviously they did something. You can see the snow, first of all a hole, and the snow is falling. Whether if it reached the ground or not, they didn't even say. But there were many anecdotes about it, because they said that the president of GE did not believe it. He thought it was nothing. So they claimed that they went once again and they drew his name in one of those stratus clouds to convince him that indeed it's working. Well, the news spread around the world. The whole world knew about it. In Australia, faraway place, Squires and Smith, and Squires was a cloud physicist, did know quite a lot about clouds. In 1947, he took an aeroplane and dropped dry ice pellets on top of convective clouds. And after 13 minutes of seeding, that's what you see here on top. And after 40 minutes, that's what happened. There's no report if rain actually fell on the ground, but it's obvious that something happened in the cloud. By releasing latent heat due to freezing, the cloud grew in altitude. Now, Langmuir was so happy with his success, and he announced all over the newspapers. In fact, the story, I must tell you, according to the book that I'm reading, he was asked to join part of the Manhattan Project at one point, but he decided that a much more effective way to fight in the military is to improve on the cloud seeding. So he decided he declined to join the Manhattan Project. But anyways, he says that these are what he saw, the spectacular results and benefits of weather control. We can change the desert into farmland. We can steer, we can move the hurricane, prevent them from hitting land. And also he had the feeling that this is like the butterfly. If you can seed something in Texas or New Mexico, and later on it's going to rain in Massachusetts. So the claims were enormous. However, even in the United States, it created tremendous discussion and disagreement between him and the Weather Bureau, and especially with the research community. They did not believe, his big claims, but, Langmuir is Langmuir. He was a Nobel laureate, and people gave him all the respect. At the same time, while all this was going on, Bernie Vonnegut in GE laboratory was trying to find a better method for seeding cloud. And he was looking for a different agent. And one of the agents that he found was silver iodide, because silver iodide has a better resemblance to the crystal structure of ice, and therefore his logic, which is somewhat correct, it could be a very good ice nuclei. It could create ice in clouds at a warmer temperatures, just below the 0 degree isotherm. The problem is that once he discovered that, I think this was part of the downfall, beginning of the downfall of many of those experiments in cloud seeding. Because commercial companies immediately grabbed onto this idea and went around the world claiming that they can change, they can make rain, they can do anything you want. This was the beginning of the commercial rainmakers. Well, the commercial sectors, what they did, they used, as you see here, this generator that produces smoke, silver iodide smoke, by burning acetone with silver iodide that is dissolved in it. And they have things like that, and they have something this big that can supposedly eject those, emit those particles into the atmosphere, into the clouds in very high concentration, and consequently will definitely change clouds. Well, as time goes on, you can see the Chinese didn't wait long. They start using cannons to shoot into the clouds with silver iodide in them. They have some airplanes that have generators on them so they can fly just below cloud base and burn and emit silver iodide. More recent development, they have flares that they can eject just below cloud base and seed those clouds. Now, at that point, we call it the heroic age of rainmaking, because the claims were that you could make rain, dissipate fog, steer hurricanes, make snow, stop hail, and stop rain. So you could do everything. Just silver iodide will resolve everything, no problems. Now, in spite of those spectacular claims in the 1940s, 50s, and even part of the 1960s, the questions were aroused, especially with the scientific evaluation. Now, total rain can vary by, a few orders of magnitude. And how can we detect changes that are maybe 10, 20, even 30% in precipitation with all these variations almost, due to wind or concentration of aerosols in the air? How can we detect the signal out of this noise? And at that point, it was clear that we need to have statisticians, professional statisticians, who design these experiments. In addition, there was supposed to be a physical hypothesis. You don't go out and see the cloud without even thinking. You have to know, at least pretend, that there's some kind of hypothesis that when you see the cloud, something will happen that will result in rain on the ground. So usually there were hypotheses, but they were never tested, never confirmed. Now, at the end of the 60s, after a number of experiments, still with no clear answer. First of all, there were in the States a number of White-Up by Bram, Arizona by Benton, Climax Project by Lou Grant, Storm Fury in Florida, and on and on and on. Reports, however, some reports of some success came from Israel. There was an experiment which I'll talk a little bit later. One thing for sure, cloud seeding in clouds do not resemble the kind of racetrack picture that Langmuir and Schäfer produced in their experiment. So it doesn't look like that. It's much more complex. Then we come into post-heroic, which is the age of enlightenment. In the 1970s, there was an improvement in instrumentation, so we could fly into clouds. We can do a much better analysis of the characteristics of those clouds. And, of course, better cloud modeling. We have some people here that will help us understand the cloud microphysics and the cloud dynamics. All those actually started in the 70s. It also became clear to all the scientists that cloud seeding of rain should be treated in a similar manner to what we do when we develop a new medicine. You have to use a control, or placebo, you have to use a target, and you have to have a certain kind of idea what the results that you are looking for. And if at the end the results do not completely conform with your hypothesis, or maybe it duplicates your confirm your hypothesis, but does a few other things, the FDA will not approve it. You have to go to do the experiment again and define exactly what kind of experiment you are doing. You know, if you're going to produce medicine for headache, you cannot convince the FDA that the same medicine will help you with a heart attack. You know, if you claim that it's good for heart attacks, you go and do another experiment showing that it improves the heart attack. You cannot expand on that. The same thing with clouds. If you see the clouds, you may get more rain, but you may change something, the duration, which I'll talk about later, or may change something else. This is not enough proof that your experiment was successful. You have to go again and do another experiment with the aim of testing the new things that you found. That makes cloud seeding that much more complicated. The WMO at that point decided, okay, now we sort of understand a little bit about cloud physics and about cloud seeding, except that so many private companies claim success everywhere in the world. So they decided already in the late 70s to start writing every few years guidelines and statements about cloud seeding. Basically, there are a number of points. There are many others, but those are the most important. The physical hypothesis must be based on known physical processes, not some ideas that you even hear today. There must be separation between the statistician and the operators, because it's very easy for if the operators knows what the statistician wanted, he is going to divert from the original plan just to prove that seeding indeed works. We need to do a confirmatory experiment. After you have done the exploratory test, you have to do a confirmative experiment to confirm that indeed the results that you got in the first trials were indeed repeated. We need direct physical measurements. The aeroplanes have to fly into the clouds and indeed show that what you did indeed interfere with the microphysical processes. And the success of the experiment basically has to do with how much rain falls on the ground. The fact that you say that something happens in the cloud, for rain enhancement, it means nothing. Rain enhancement means you have more rain on the ground. The way to do it, one way, one of the most common way, is what we call the double ratio. We take a control and we take a target and we look at how much rain fell. We have here. T is the target, so this is day that was seeded in the target over the day that was allocated for seeding in the control, divided by the target, which is unseeded, and over the control unseeded. So you sort of erase biases by this method. Okay, now I come to the Israeli experiment. Now, why do I come to the Israeli experiment? Because it is the longest running, it's not a longer, it's a number of experiments that have been going on in Israel for over the years. And as you see, you will see it was considered a big success, but with some caveats. The first Israeli experiment was from 1961 to 1968. It was done the following way. This is the target area, and this is the target area, and this is a buffer zone which is unseeded. An aeroplane flew along this line, seeding, hoping that the wind will carry the particles into the target area and enhance the amount of rain falling there. At the same time, also an aeroplane flies here, hoping that more rain will form here. Now the experiment, the statistical experiment, was done in the following way. At the beginning of the season, they took a lottery, and they said, or dice, they threw the dice, and they said, let's say the 1st of December, we are going to seed in the north. The second, the dice say, okay, also in the north. And the third, in the south, and so on and so on. They mapped the whole season, the whole winter season. Now, of course, it's possible that the 1st of December was supposed to seed here, and there were no clouds, so they didn't seed. And if at the same day, for example, there were clouds here, but not here, if the allocation was for seeding here, you don't seed. You simply wait for the proper day. Now, they compared the amount of rain in this target to the number of rain in this target. There was no control. In fact, every time you seeded here, this was the control, and vice versa. Okay? And at that point, some of the results suggested a 15% increase. But because they compared the north to the south, they couldn't actually tell whether it was in the north, 15, or in the south, or maybe in both of them. It was not clear which part is actually which part gained the amount of rain. In addition, since this was the target area, there was a statistician from Colorado State University who analyzed the amount of rain falling in the Syrian heights here and claimed there was an increase in rain in the Syrian heights due to the seeding here in the north. Now this is maybe true, but definitely not part of the original experiment. Okay? In addition, this particular experiment was very controversial by a number of scientists and statisticians in the States because the definition of a day, seeding day, was changed in the middle of the operation. So consequently, you couldn't actually analyze it properly. And there were very prominent statisticians in the States who violently opposed to this particular result. Then there was another experiment called Israel 2. Now this was after the 1967 war, and Israel gained control of the Golan Heights and also this area here in Samaria in Judea. So now the experiment was, the flight was along this line, making this area here as a control. So now the comparison was between the target area and the control that was here. In addition, there was another seeding line here, and the amount of rain falling here was compared to the control area here. Okay, let me just briefly say the objective here was to try to increase the amount of water flowing into the Sea of Galilee, which is the biggest reservoir that Israel holds. Okay, so this was the objective. The results of this particular experiment showed about 13% increase in the north of Israel. However, there was no increase in rain due to seeding, at least statistically, in the south. Now, at that time, the Israeli experiment was considered a success story. Langmuir was probably very happy. Fantastic success story. Now, because why was it successful? Why it was so considered a success? Because the original hypothesis was that the clouds in Israel are continental. I don't know how many people here know what it means. Continental means that the clouds have high concentration of cloud drops that compete with each other so they cannot grow very effectively. Usually the size of the droplets does not exceed about 10 or 15 micron at the most. And also the ice crystal concentrations in this particular cloud is usually very low. So these particular clouds are, by the terminology of the people who seed clouds, those are seedable clouds, which means if we can put more ice, because ice grows faster than water drops, the ice crystal will grow very fast, they will collect water drops, and eventually fall down as rain. So the more ice you put into the cloud, the chances are you're going to increase the amount of rain in the cloud. So some of the early measurements using very primitive method of measuring drop size in ice crystals indicated that it's possible that the Israeli clouds are indeed continental and they don't have enough ice in them. Also, the statistical results I showed you indicated success. And there was some supporting evidence. Some people looked for water, increase of water on the ground. They looked for the flow in very small springs, and they found, not statistically significant, but they found what they called enhancement in the flow. So here we have big success. Well, with this big success, they tried to duplicate the same experiments, both in Spain and later on in Italy, and these experiments were not successful. In fact, I was involved in the experiments in Italy, in southern Italy, in Puglia, and nothing. There was nothing there. In fact, we stopped the experiment before the end of the 6-year period because we felt it was a waste of time and money to do it. Now, following the second experiment, the big success that Israel reported, in 1975, the water commissioner at that point decided that it doesn't cost him that much money, may as well go ahead and do cloud seeding on an operational basis. Every time there's a cloud or storm comes in, you go out and seed it. That was the idea. Now, the result from the statistical analysis during the period by Nir Ellen Rosenfeld showed a decrease in the effect of seeding, something about 4% only, as compared to 12 that was originally. A few years later, Kessler et al. In 2006 found that the seeding had absolutely no effect whatsoever. Well, he didn't stop the water commissioner, he kept on supporting it. So now we go into reanalysis of these particular operations. First, I will look at the physical hypothesis. Is this correct for the Israeli clouds, for the ones that were seeded or not? Well, we used an airplane. This particular airplane, by the way, some of this facility was for the MADEX experiment that was mentioned for the flight during the shuttle experiment, the Columbia shuttle. But many of the instruments on board were the same ones we used for our analysis. And one thing, this is something we published already in 1996. First of all, this is a flight every second, the size distribution as you cross the clouds, about 100 meters above cloud base. And you can see that the drop size distribution in some cases is even 40 or 35 microns in size. Definitely not what one would expect in a continental, what we call a pure continental case. More recent study by Amir Givati and Danny Rosenfeld, also in the same area that we did, this is 2010, you can see the different elevations in the cloud, even at the lowest level. Already we have drops that are fairly large and grow very rapidly with altitude. Again, not something you expect in a continental cloud. Now, why do we get such large drops in cloud base? Well, partly we have dust particles in the air most of the time in Israel. Not that you don't have to have a dust storm. We get dust particles. They are coated very often with sulfate, Sometimes they are impacted by sea salt, and when these get into the cloud, the soluble material, the sulfate of the sea salt, will produce what we call giant cloud condensation nuclei, producing relatively large drops. And these are the drops, we think, the drops that we see in the tail of the drop size distribution. Now, this was regarding the cloud drop distribution. Now, here I have a table also for measurements, a number of measurements in the 1990s. And you can see different temperatures that we fly in. The concentration of cloud drops on the average about 350 to 400. It's not a maritime cloud, but definitely not what we call a continental cloud. And the most important part is, look at, these are the temperature, 10 minus, this is the number of ice crystals that we observed. Considerably higher than what would one expect by simply looking at the literature and expecting at about minus 10 or minus 21 per liter. Here you get a few orders of magnitude more ice crystals. So maybe the question is, if we add more ice crystals, maybe we'll actually prevent or reduce the amount of rain that we get on the ground. So something about the hypothesis, the original hypothesis, and you remember, this must be correct. The hypothesis must be confirmed in order to understand what the results mean. So the rain clouds over the seeded areas in Israel are not strictly continental. They contain lower drop concentrations than in pure continental clouds. They contain a number of large drops, as I showed before, that accelerate the growth by collection. Ice crystal concentrations are also very high. Now, we also did a model calculation because the Israeli system is, the aeroplane flies along a line. He doesn't know if it's raining or not raining. It may rain overhead, but he keeps on releasing silver iodide. So we simulated a storm, three-dimensional, and we allowed a plane to fly, supposedly, in the computer and release silver iodide. Most of the particles were washed down to the ground, did not even reach any height in the cloud. So even the method that is used by flying along a line, usually at cloud base, is not very effective. So this was about the physics. Now we wanted to know the statistics. Can we understand? I mean, there were some statistical results showed some. So we published a paper that actually looked at the statistics, but looked at the operations, whether they were affected by the synoptic conditions during seeding. And what we did is we took Israel 2 experiment. This is from 1969 to 75. We took it as one set of data. And then another one we call the full period, which goes from 1950 to 2007. Now remember, before 69, there was the Israel 1. So we did not consider the cases where seeding was done in Israel 1, only unseeded. So from 1950 to 69, only days that were not seeded. 69 to 75, seeding based on the experiment, your randomized experiment. From 75 to 2007, every time there's a cloud or a system, seeding was done, okay? So we had huge amount of data which we can compare. And we looked at the double ratio, this method that I mentioned before, to understand what's happening. Now this is a little bit complicated. I'll try to go very slowly here. This is Israel 2, all the allocated days, because as I said before, there may be a day that was allocated, as the December one was allocated for seeding, but was not seeded because either there was no rain, no clouds, or maybe the aeroplane didn't work. Something happened to the airplane. So this included all the days that were allocated for seeding. This is the days that were actually seeded. And this is the full period from 1950. And you can see the distribution of rain. You know, you get a maximum here, you get a maximum here and here. This is the unseeded days during this whole period. And this is the most important, and this is the double ratio. You see, we get about 1.12 average double ratio, which suggests a 12% increase in rain in the full period, in the allocated days, 70% increase if you only take the allocated days for seeding, and if you look at the full period, which you have much more data, seeding has no effect whatsoever. Why? So, as I said, during Israel 2, the mean of the double ratio is larger than 1, which means it was successful. And during the full period, when you include all the days, it's not successful. Well, we decided to look at the synoptics, and we divided into 3 types of conditions. One of them, when we have no lows, which means clouds developing without any specific, very strong front coming in. The second one is what we call shallow lows. Usually those are clouds that maybe reach about minus 15, minus 17 degrees, and deep lows where they go to probably minus 20 and more. And what you see here, this is Israel 2. This is the experiment between 69 and 75. I just want to point out that 41% of the big clouds were seeded, and also 34% of the middle clouds were seeded. The unseeded, the big clouds, only 28%. So very big emphasis was put on seeding. This was supposed to have been a randomized experiment without knowing if it's a big cloud or a small cloud. But you see, it's called I think they call the statistician call it the error 1, or type 1 error in statistics. And you see, so preferentially they didn't seed the big clouds. The amount of rain that you get, of course, you get more rain coming out of the big clouds and from the middle clouds. If you look at the full period, on the other hand, you see 40% seeded, 29 seeded, about the same amount as here. However, you get 41% of the rain as compared to 36%, and the unseeded is considerably lower. Also, the wind, it turns out, during the seeding days, the wind was stronger, and there were quite a lot of papers showing that increase in wind speed enhances the amount of rain on the ground. So seeding was preferentially done on days associated with deep lows and stronger winds. In the full period, which was dominated by the operational periods, remember, seeding was done on almost all rainy days, including 45% of days with shallow lows, lowers the double ratio to 1. Now, what we have here is preferential seeding in deep lows. It was not part of the original design. The original design was you seed, you have a certain criteria, cloud top must be at least minus 8, and you cannot go and seed only these clouds that are very, very tall. Basically what it says, you have to do another experiment. And next time you can say, okay, now I'm going to seed only the very big clouds. Although from this experiment you can say, oh, I have a hint that seeding those big clouds will give me more rain. That's okay. But it's exactly like if you have a medicine and for headache and somebody tells you it's good for heart attack or for cancer, you say, wow, it's fantastic, but no, you cannot use it. You have to go and do another hypothesis and another experiment. Same thing here. We wanted to test something else. Let's look in this one, I think it's more important. We took the days in Israel 2 that were seeded along the line here. This is the target area, and this is the control. And we artificially took a control area along the coast and a target area here. At the same day that was seeded here, we assumed that it was seeded here too. Okay? We assumed. Actually, it wasn't seeded, but we wanted to assume that it's seeded. And look at the double ratio. Here it's 1.13, which is similar to what I showed before. And down here, it's 1.15. What does it mean? What does it mean? That cloud seeding actually decreased the amount of rain in the north because there was no seeding done here. So the double ratio in the center of this, to the south of the target area in Israel 2, is greater than the one in the experimental area. Now, based on these results and a few other results that I didn't go into, the Israeli Water Commission finally is rethinking the whole project. Rethinking about the project, and a new experiment is now being planned. It was supposed to have started last year, but because of other problems it did not start. But basically the idea is to shift the seeding line eastward and take advantage of the lifting of the clouds over the Golan Heights. You know, enhance the rain through the orographic effects. Whether it's going to work or not, we don't know, but this is a new experiment. At the same time around the world, there's a new look at hygroscopic seeding. You have to understand, hygroscopic seeding used to be a method that people used, especially in India, to increase precipitation in warm clouds, clouds that don't contain ice at all. And the results there are somewhat similar to what the results with glaciogenic seeding. Also, we don't know if they're successful or not. However, if in cold clouds, clouds that contain ice, we increase the size of the cloud drops, there's a better chance that some of those cloud drops will freeze faster than if they wouldn't grow at all or stay very small. So the idea was to seed clouds with flares, these pyrotechnic flares, producing very large number of tiny little soluble particles. And the whole idea actually started in South Africa. They flew an airplane measuring things in clouds. And at one point, they flew over a paper mill, and they observed that the cloud droplets are wider than in areas that are farther removed from the plume of the paper mill. And they tested the paper mill, and they found it to be a very good cloud condensation nuclei, a giant cloud condensation nuclei. And at that point, they said, well, lo and behold, we can seed the cloud artificially. With this kind of particles, it will produce larger drops, and eventually will produce more rain. And here are the flares that they developed at the time in South Africa. And this was a randomized experiment, which was something new, because they used radars to evaluate the progress of the development of the cloud to formation of rain. They looked at about 6,000 feet at the area of the reflectivity and followed it as a function of time after seeding, and interpreted the amount of rain on the ground from these radar measurements. Now we all know, people who deal with radars know that there are quite a lot of errors with radar measurements, especially interpretation of rain. And if you're expecting 10% increase in precipitation, depending on radar, to give you a good estimate of amount of rain on the ground is a little bit dangerous. Except that this particular program, it's called Titan, was developed originally in South Africa, then at NCAR in America, allows you to identify cells which are called control and cells which are called seeded, and they follow both of them as a function of time. And this is something I got from Brent Foote, and you can see here, this is the cloud, and they look at the 30, this is the cloud here, and they look at the 30 dBz, this is the reflectivity, and they follow the cross-section of this one as a function of time. The only problem is that sometimes these clouds merge with one another, and you have to interpret these also in your analysis. This is the kind of things that they see. This is one, and this is two, one control and one seeded cloud. These are the results that they obtained. Seeding was done here at 0, although their radar is following the clouds all along. This is the control, the red. This is the blue, is the seeded cloud. These are the 75% and up, the biggest cloud. You can see that they get much bigger interpretation of rain from the radar. This is true also for the middle and also for the small clouds. But one thing notice, the duration of the seeded cloud is much longer. Again, something which was not envisioned in the hypothesis. But it's very promising. Now, in order to do it, you have to do a confirmative experiment. Well, money ran out, and this was the only experiment. There was no confirmatory. However, they did some measurements, and the measurements show that the drop size distribution that was originally like that, after a while became like that in the seeded cloud. And they ran numerical models, and they show a widening of the distribution as a result of these flares of hygroscopic particle. This, of course, generated a tremendous amount of interest around the world. And Mexico decided to pay money to NCAR to do an experiment in Coahuila, I guess it's called. And look at the results. By the way, here they use the same airplane, the same operators, the same pilots, exactly the same thing that was used in South Africa. And the results are similar. You see the seeded cloud produce more rain than the unseeded cloud, but again, the duration is much longer. Now, why could it be, again, speculation? Because if you produce rain in one cloud, and the cloud, if you produce rain in one cloud, and the rain falls down, it cools the air below the cloud, and as a result, it will produce a secondary cloud, sometimes very close to it. So if you look at the radar, you integrate over the whole area, you include in the second time also the two clouds together. And that's possibly, it's not 100%, possibly the reason that the duration is increased. But this is not something that has been confirmed. Now, confirmatory experiments, as I say, in South Africa and Mexico were never performed. And similar experiments in other countries, like I know in Indonesia and others, were not successful. Now, the question is, can hygroscopic seeding be successful everywhere? The fact it was there? Well, this is just an example of a study that we did, nothing to do with this particular experiment, but I think it indicates something very interesting. This is the cloud condensation nuclei, which means basically the more polluted you are, the total precipitation on the ground decreases, okay? Look at the red line. The more polluted the cloud, the less rain will fall on the ground. But what happens if you add this giant cloud condensation nuclei? This is the green one. Up to about 600 or 650 particles per cubic centimeter, changing adding giant nuclei will not make the rain stronger or more rain on the ground. However, if you take a very polluted case, then the giant condensation nuclei will make a difference in the amount of rain. Of course, the total amount of rain is relatively small, but still, you increase it over the reference case. The interesting thing here is also what happens in the same cloud, you increase the amount of ice that you have in it. This is the blue line here. You can see that in the clouds that we have in Israel, which is around here, if you add too much ice, this is 10 times more ice. If you add too much ice, you actually decrease the amount of rain, not increase. So you have to be very careful what you do. So in conclusion, glaciogenic seeding, has not produced the expected results. And the high positive results in the Israeli experiments was largely due to unintentional selection of favorable conditions, synoptic conditions. Hygroscopic seeding holds some promise, although all the experiments show changes in the duration, as I said, and this requires another experiment. Now, more tests are needed. What are the challenges? Well, cloud seeding is still not a proven technology, this we can tell. The atmosphere is complex, with many unexpected feedbacks that affect the final outcome of seeding. Cloud seeding methods cannot be transferred without prior measurements and classification of the local conditions. You cannot just, like in Italy, take the Israeli method and expect it to be the same result. Seeding without prior knowledge of the characteristics of local conditions And pre-designed randomized experiment could be just a waste of money. That's something that the water manager should know. Now the opportunities. Well, there is potential for successful cloud seeding in orographic clouds. That has to be proven. But at least those clouds are not gigantic clouds, and possibly some interference in the growth of the particles in them could lead to more precipitation. Still not proven, as I said. Now, seeding with hygroscopic particles has shown some promise, but more experiments are needed. Now, before I conclude, I want to say that I had to. If we do not understand the effects of cloud seeding, which is actually geoengineering on a small scale, how can we understand the effects of many of the proposed large-scale geoengineering projects for mitigating climate? And I showed here the picture of one of my friends, John Latham, just to show what I feel about it. Now, the last slide. This is a message to the people or companies that claim success in cloud seeding. And this is something that I took really from the history. Actually, I took it from the Bible. In Hebrew, it's called Nesi'im v'ruach v'geshem ayin, ish mitalel b'matat sheker. This is from the book of Proverbs. And it says, one who boasts of a gift that he doesn't give is like clouds and wind without rain. Thank you very much.